So in our chemistry session this week, we're continuing to think about electrons in atoms. And the reason we need to think about the way electrons are arranged in atoms is because you know from your GCSE course that electrons in the outer shell really affect the way an element will react. Well, we're going to meet today the three important words shells, and shells are marked out with numbers 1, 2, 3, 4, etc. Then we're also going to find out that these shells are subdivided into subshells, and subshells have letters S, P, D, F, and there are further letters beyond them, but we have not yet discovered any elements big enough to fill higher subshells. And then finally, orbitals. Subshells are chopped up into smaller things called orbitals, and an orbital is a region of space that can contain 2 electrons. And the 2 electrons are very commonly represented like this: an arrow going up and an arrow going down. Each arrow is an electron. So as an example, here we see calcium. Calcium has a mass number of 40 and an atomic number of 20, so an atom of calcium has 20 electrons. Now, no doubt your GCSE teacher quite rightfully told you that therefore her electron configuration would be 2, 8, 8, 2. Now, I would put it to you that what you learnt at GCSE were shells. That you learnt that there were 2 electrons in shell number 1, 8 electrons in shell number 2, 8 electrons in shell number 3, 4 electrons in shell number 4. And at that point you never went any bigger, for good reason, by the way, because beyond this point of calcium things get more complicated. I would say now that actually each shell is subdivided into subshells. Shell number 1 is divided into an S subshell. Shell number 2 into an S and a P subshell. Shell number 3 has an S, a P and a D, but the D subshell is empty at the moment, so it's not included. And shell number 4 has an S subshell. So the better way of writing 2, 8, 8, 2 is like this: 1s2. The 1 means shell number 1, S is the subshell, and the superscript 2 means 2 electrons. 2s2, shell number 2, S subshell, 2 electrons. And then shell number 2, 2p6, P subshell, now there are 6 electrons, etc, etc. This is an electron configuration as it is written at A level, and reveals more about the nature of calcium because we learn that the outer electrons are not just in shell 4, they're in an S subshell. Now let's meet a slightly more complicated example from the middle of the periodic table, the bit that a lot of teachers incorrectly call the transition metals. We meet iron. Iron has 26 electrons in her atoms. So here, let us think how these 26 electrons are put into the atom. Well, what I've done is, rather than write the subshells in a straight line, I've put them on an energy level diagram. So you can see the lowest energy shell is shell number 1, subshell S, where I have put 2 electrons. There they are, the 2 arrows in the 1s. Then there's 2s, and there's 2, then 2p, and there are 6. Then in shell number 3, we're at 3s and there are 2. Then 3p and there are 6. Now, what you may think is that the next thing to be filled is 3d, but actually in terms of energy, 4s is slightly lower in energy than 3d. So we fill the 4s subshell and then come back and start to fill the 3d subshell, but there are only 6 electrons in 3d because by that time you have allocated all 26 electrons. Therefore the final configuration for iron is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d6. Some books and some teachers may teach you to put 3d written before the 4s. It doesn't matter. It really doesn't matter which way round you put them. Exam boards accept them either way round, This is the way I was taught it, so I do it this way. But other teachers will teach it the other way round. Therefore, we see that the outer electrons of iron are in a D subshell in shell number 3, and there are 6 of them. 3d6. That's why iron behaves very differently from, say, calcium. Its outer electrons are in a very different place. To see how the A-level model provides more data than the GCSE model, here we're going to pick on an old favourite, sodium. She has 11 electrons, and undoubtedly were made to draw pictures like this over and over again throughout your GCSE course, telling your teacher that sodium had 2,8,1, and that was the configuration of her electrons. But if we think a little bit deeper, we say that those 11 electrons are actually in different subshells. 1s2, 2s2, 2p6, 3s1. So 1s2, shell number 1, subshell S, has 2 electrons. 2s2, shell number 2, subshell S, has 2 electrons. Shell 2p6, shell number 2, subshell P, has 6 electrons. 3s1, shell number 3, subshell S, has 1 electron. And that's really where the 11 are. Now if we think even deeper and ask about orbitals, an orbital is a region of space that can hold 2 electrons. So therefore an orbital is represented as a box with 1 arrow going up and 1 arrow going down, and each arrow represents an electron. So we fill from the lowest energy going up. 1s, there's her 2, 2s, and there's the 2 electrons, 2p, and there's the 6 electrons, 3s, and that's only got 1, so it's not full, 3s with 1 electron, and that is the most useful electron configuration of the way electrons are arranged in sodium. So in our final step, let's see how we can work out these configurations quickly and easily from the periodic table. Now you may remember in the periodic table that a group in the periodic table is a column, and any atom that's in the same column as another atom will always have the same number of electrons in their outer shell. We then have periods. A period is a row going across from one side to the other, and in a row you always fill in the same shell. Now finally we have things called blocks. So S, P, D and F blocks. This means that all these guys in the S block, their outer electrons are always in S subshells. So they're actually enormously similar one to another. All the guys in the P block, their outer electrons are always in a P subshell. D and F. All the F block elements have outer electrons in an F subshell. Hence this bit in the middle, that's often called, incorrectly, the transition metals, really should be called the D block elements. By the way, the transition metals are merely a subset of the D block, so not everybody in that block can be classed as a transition metal, which is why the term is often incorrectly used. So there we go. The blocks of the periodic table, and another way of looking for order in chemistry. Because if you do not look for order, then what you find is you have 118 different elements, and you're trying to learn a series of facts about every one of them. Well, your memory has got to be a lot better than mine in order to do so. I don't look for facts, I just look for patterns.